In this video, I want to continue talking about the symmetric group, and in particular explain cycle notation, which is a much more compact way in place of this unwieldy notation we saw last time. So let's do this by an example. And this says, express the permutation sigma given by this permutation here of the set of numbers consisting of 1, 2, 3, 4 all the way up to 8 as two things. One, as a product of disjoint cycles, and secondly, as a product of transpositions. Okay, so I'll have to explain what cycles are. And let's first remember, what is sigma? Sigma is an element of S8. First of all, this is a huge group. It has 8 factorial, or that turns out to be 40,320 elements, and sigma is just one of them. It's a function, not a number, and it sends 1 to 3, 2 to 1, and so forth. And so here I've drawn schematically what's happening, or what sigma is. It's a function. The input is a set A consisting of numbers 1 through 8. The output is also the same set A consisting of numbers 1 through 8, although I was just lazy and wrote only 3 of them. And this sigma sends 1 to 3. That's what this notation up here means. And then it sends 2 to 1, 3 to 4, and so on. So I didn't bother writing it all out. Okay, and then let's try to answer this question of expressing sigma as a product of disjoint cycles. Here, down here, I've just copied sigma again from what it was upstairs. And okay, so the answer, we can just write it in one line. And here's what happens. We start with a number like 1, just start with 1, and see what sigma does to 1. Sigma sends 1 to 3, so we write that number next. Then ask, what does sigma do to 3? Well, go over here, and sigma sends 3 to 4, so then we write that number next. And we just continue that process. Sigma sends 4 to 7, so we write down 7 next. 7 goes to 8, then 8 goes to 6, so then we write down 6. 6 goes to 5, and then finally sigma sends 5 to 2. And then what does sigma send 2 to? It sends it back to 1. And so instead of writing 1 again, this is the first time we've encountered a number that's already been written down. And so we close the cycle. Now in this particular example, it just by coincidence happens that we've encountered all the numbers. 1, 2, 3, 4, 5, 6, 7, 8. All the numbers in our set A. And so this element has only one cycle. We'll do another example shortly where there's more than one cycle. Now you might have asked, well, how do I know to start with number 1? Just start with any number, and 1 is a good choice. And when you close your cycle, then start with a number that hasn't appeared. Start a new cycle with a number that hasn't appeared, but because all the numbers have appeared, we don't start a new cycle in this particular example. Okay, the second part of the question was express this sigma, which again, this is now the cycle notation for sigma. Notice that it's much more compact. We just write it down in one line. It has the same equivalent information as this mess here. Okay, now a transposition is a cycle of length 2. In other words, it's a function that sends A to B, and B goes to the A, the thing at the beginning. So in terms of a picture, A goes to B, B goes to A, and things that aren't listed get sent to themselves. That's a feature of cycle notation I probably should have mentioned. Okay, so I've copied over what sigma is, and we've got to express it as a product of transpositions. There's many ways to do this, and here's a trick that gives one way that works in general. So the idea is you just start with the first element listed in the cycle notation for sigma, which just happens to be 1, and then you work backwards and write 1, 2, make that as a cycle, then start a new parentheses, 1, the next number from the last one, which is 5 in this case. Close that transposition, and then so on. 1, 6, 1, 8, and so on, and stop at 1, 3. And again, this is just a trick. This is just one way to answer part 2, which was write this element sigma as a product of transpositions. This boxed answer is a product of transpositions. Remember, a transposition is just a cycle of length 2. Length just means the number of numbers appearing in a cycle. So this cycle here has length 8, because if you just count up how many numbers there are, there is 8. Whereas each of these cycles is length 2. Okay, so why does this trick work? Well, we have to see or show that this product here sends 1 to 3, 3 to 4, 4 to 7, and so on. So let's see what it does to 1. Because function composition works from the right to left, we have to start with the 1 out here. So that's what's happening down here. I ask, what does 1, 3 do to 1? Well, it sends 1 to 3. So 1, 3 applied to 1 sends it to a 3. And then I have to ask, what does 1, 4 do to the 3? And 1, 4, that just interchanges 1 and 4, switches them. It doesn't do anything to 3, it leaves 3 alone. And so that's what's happened here. Then I ask, what does 1, 7 do to the 3? It doesn't do anything to 3. And you can see that because there's no 3 appearing in the rest of the way, what will happen will that 1 will end up at 3. So that's what I've drawn here, that eventually 1 does go to 3. Then we ask, well, what does it do to 3? Well, we then start with 3 out here again. That's down here, or out here. 1 and 3, the transposition 1, 3 switches the 3 to a 1. And then we ask, what does 1, 4 do to the 1? It sends it to a 4. And then we ask, well, what does 1, 7 then do to a 4? And you can see that 4 doesn't appear the rest of the way. And so the point is that 3 goes to 4. And that's exactly what sigma does as well. And so these two elements of the symmetric group agree on what they do with 1, agree on what they do on 3, and you can believe then that they agree on what they do with all these other elements. Okay, moving on to another example. Just a comment is that in S3, it's a non-abelian group. In other words, the order in which you multiply matters. Here's a simple example. Let's multiply 1, 2 and 1, 3. These are 2 cycles, or 2 transpositions even. And let's write down what they are in cycle notation, what this product is. Okay, so we open parentheses and start with an arbitrary number, typically 1. And what does this element of S3 do to the number 1? Well, we start imagining 1 on the right here. And then 1, 3 sends the 1 to a 3. And 1, 2 doesn't do anything to the number 3. So 1 gets sent to a 3. Then we have to ask, what does this element do to a 3? Well, imagining 3 here, 3 then gets switched over to 1, and then 1 gets switched over to 2. So 3 goes to 2. And then finally, we ask, what does 2, where does 2 go to? 2, well, this doesn't switch or do anything to the 2. And then this switches the 2 to a 1. So this 2 goes back to 1, and we've completed the cycle, so we close our parentheses. Okay, now another way to write the same element is 3, 2, 1, because 3 goes to 2 and 2 goes to 1. So the cycle notation isn't unique, but it is unique up to cyclic shift. So what I've done here is I've taken 1, 3, 2 and just moved over the 1 that way and then moved everything to the left. Similarly, I can move the 3 over to the end and move everything to the left. So these cycles are all the same element of S3. On the other hand, let's look at 1, 3 multiplied by 1, 2. I should have commas in between here. Okay, so if you do the same analysis, you see that this product here is the cycle that sends 1 to 2 and 2 to 3. let me just quickly check the 1. 1 goes to 2, and then 2 doesn't get messed up by this, and so 1 does indeed go to 2. Now, these two cycles are different elements of S3 because this element here sends 1 to 3, whereas this sends 1 to 2. So because 1 goes to different things, these are different functions and therefore different elements of S3. And so S3 is not abelian because we've just swapped these two transpositions and computed the product and found that they're not equal to each other. Abelian is the same as commutative, and so S3 is not commutative. And in general, S3, S4, S5, so on, they're not commutative or not abelian. S2 is commutative, but that's a very small group consisting of just 2 elements. Okay, let's do another example of expressing an element of sigma in cycle notation. This one will be an example where there actually will appear disjoint cycles or more than one cycle in the answer, unlike the first example that I did. Okay, so sigma is this element here. This is different from the first example that we did. And again, the question is, write sigma as a product of disjoint cycles. Disjoint means no number appearing in more than one cycle. Okay, so, well, we start off with open a cycle and ask what does 1 go to, or sorry, begin with 1 and ask what does 1 go to. Well, 1 goes to 3, so then we write down 3. Then ask what does sigma do to 3. Well, here's 3, sigma sends it to a 6, so write 6. Then we ask what does sigma do to a 6. Well, sigma sends 6 to a 1. Now, instead of writing 1, because we've already seen 1, we close this cycle. So that's sort of the name for the term cycle, is 6 cycles back to 1, 1 then goes to 3, 3 goes to 6, and so this permutation sigma is cycling these numbers amongst themselves. Okay, so then we start a new parentheses because not all 8 elements, 1, 2, 3, 4, all the way up to 8, have appeared or have been analyzed. So, okay, let's start off with a number that doesn't appear. I could start off with any number that hasn't appeared amongst these 1, 3, and 6. I don't want to choose 1, 3, and 6. Those are already understood. So I could choose 2, but just to be different, I just chose 4. Okay, so, well, what does sigma do to 4? It sends 4 to a 7, and you just continue the process. 7 goes to a 5, 5 gets sent to a 4, and 4 has already appeared in this cycle, and so it will, what you want to do then is close the parentheses. You won't see a number that's appeared in a different cycle already. So if you do, then you've made a mistake. It's only a number that is in the cycle that you're currently within or in could possibly reappear. Okay, so then we still haven't exhausted the numbers 1 through 8, so then we open a new cycle and start off with a number that hasn't appeared yet. 2 has not appeared yet, so I ask, okay, what does sigma do to 2? It sends 2 to an 8. What does 8 go to? It goes to 2, and then I close that cycle. Okay, so this is one answer. And again, there is some ambiguity, not a whole lot, but there is some ambiguity in the cycle notation, namely that you can cyclically permute the cycles. And then also, disjoint cycles are commutative. And so the order that you list these disjoint cycles in doesn't matter. Okay, so for example, the book's answer was this, and this is the same element in the book gave that we found. Why is it the same element? Well, certainly 136 and 136, they're the same. 475 and 475, they're the same. 28 and 28, they're the same. But the order, usually the order matters. But if the cycles are disjoint, in other words, they don't have any overlapping numbers, then you can move them around. And so that's why the answer we found here and the answer we found here, or the book gave, are the same. Again, another possible answer was if you flipped or switched the 8 and the 2. So instead of 2, 8, you wrote 8, 2. That would also be a correct answer. Okay, and so this is the fact that I've kind of mentioned, that even though Sn is non-abelian, in other words, not commutative, disjoint cycles, again, disjoint means having no number in common, they do commute with each other. And for example, 2, 8 and 4, 7, 5 are disjoint cycles because there's no number in common. And so when you think about it, you can even realize that the way that you multiply them or compose them, these two functions, doesn't matter because they mess up different numbers, if you will. The 2, 8 messes up or switches just the 2 and the 8. The 4, 7, and 5 only messes up the numbers 4, 7, 5. And so the order, because they're disjoint, the numbers that you mess up are different in each cycle. It doesn't matter which order that you apply these functions in.